Today I'm going to introduce some concepts that will help us understand the electronic structure of the atom. In other words, where are the electrons in the atom? There's a lot of history behind this, and it's useful to study this because it gives a really good picture into how scientists think and how scientific knowledge is developed. And as we study the electronic structure of the atom, we're actually going to take a really close look at a model that later on turned out to be faulty, but it's a very good introduction to the idea of quantum phenomenon, the idea that things on the small scale really don't behave the way they seem to on the large scale where we observe them every day with our eyes. To understand the electronic structure of the atom, we have to understand something about light and other forms of electromagnetic radiation. To understand that, we have to understand a few things about vibrations and waves. So let's make some definitions. A vibration can be thought of as a stationary periodic disturbance. So something, it could be matter and it might not be matter, is disturbed but in the same place, and it's periodic, so over and over again. So when I do this, go back and forth in the same spot, up and down, 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 I'm vibrating my pen on my tablet here. It's stationary, it stays there, and it happens every so often. It's pretty regular, and I'm disturbing, I guess, the position of my pen on the tablet. To describe a vibration, one of the things that you need to describe is the frequency of the vibration. Frequency is just how often does a repeating event occur. It's symbolized by this letter that looks sort of like a V with a tail on it. It's a Greek letter and it's pronounced nu, so that's frequency, how often something occurs. The SI unit of frequency is the Hertz, named after Heinrich Hertz, and the abbreviation is capital H, small z. And a Hertz is 1 per second. So 1 cycle per second or 1 vibration per second, that's a Hertz. A wave can be thought of as a traveling periodic disturbance. So if this is a vibration just going up and down on my tablet, when I start to move across the tablet, that vibration turns into what we could call a wave. The disturbance is now moving through space. Waves have a length. It's called the wavelength. The wavelength is the distance from a point on a wavefront to the exact same point on the next wavefront. So for example, starting from here, I can go through the entire sequence and end up at the next exact match for that shape. And the distance here is the wavelength. Wavelength is symbolized by this little letter here. That's a Greek letter, and it's pronounced lambda. So frequency is nu, and lambda is wavelength. I can pick any spot on my wave, like here, and go 1 forward, and I can get my wavelength. And my wavelength will still be the same. Or I could pick here and move 1 wavelength forward to there, and the wavelength would be the same. The amplitude of a wave is the maximum deviation from the 0 position. So the 0 position is where we cross the axis here. These are 0 positions. The maximum deviation from that position is our amplitude here. And on this scale that we see here, it looks like our amplitude is 1, either plus or minus. We can think of this as the height of the wave. The frequency of a wave is the frequency of the vibration that caused it. Or another way of thinking about it is, if I were to stand right here at this spot and watch the waves go past, as this wavefront moves past here, every time I see a complete cycle go past me, I could make a count, and that would be the frequency. Waves are traveling through space, and so they have speed. The speed of a wave is the product of the frequency of the wave and the wavelength. One way of thinking about this is, imagine a train. If I have cars going past, and the cars are all identical in this train, and each car is 10 meters long, like from the hitch to the next hitch is 10 meters, and the frequency of cars going past me is, let's say, 1 Hertz, which means 1 per second. Well, since 10 meters of car length is going past me every second, the speed of this train must be 10 meters per second, 10 meters every second. So wavelength, or car length in this analogy, times frequency, how often it happens, gives me speed. And that's also true for waves. Wavelength times frequency gives me speed. Charged particles generate an electrical field when they're accelerated. So what is an electrical field? I'm going to place a positive charge on this space here, and I'm going to put a negative charge on this space. Now what you see if you look at this is a bunch of arrows, and these arrows represent the pull on a positively charged particle that's placed anywhere in this space. So if I were to move to this spot right here, for example, that would tell me that that particle would be moved kind of up towards the upper right hand corner. Or down here, this particle would be just moved down towards the lower left hand corner. And in general, if you follow these arrows, it looks like the arrows are going from the positive to the negative, and in fact that's what's happening here. I'm going to grab a little positively charged electrical field sensor and put it in this space. Now this is going to have an arrow attached to it that shows what direction and how strong is the pull on this particle. I'm going to take all the arrows away to make this a little clearer. As I move this around, you can see that where this thing is attracted to changes. As I move it close to the positively charged particle, that field gets really strong and points away. As I move it towards the negative, it gets strong and points toward it. So the field is sort of this invisible grid of changing poles on that particle. So if I place this positively charged particle there, and if I were to let it go, the arrow is showing, would have a tendency to move toward the negatively charged particle. Well, we know that opposites attract, and so that would be clearly the case. I'm going to start out again with the simple, just one negatively charged particle, like an electron. And watch what happens to the field as I move this particle around. The motion of that particle changes the direction of the field, and it also changes the size of the field in a particular location. So by accelerating a charged particle back and forth, I can generate a change in field. Well, electrical fields are just one kind of field. Another invisible force that we can sort of track, and it looks very much like this, is magnetic force. A magnetic force field exists between not positive and negative, but north and south poles of a magnet. And you can set up field lines or field arrows like this, and you can generate magnetic fields. But magnetic fields are not only generated from magnets, but they're also generated from electrical fields. When there's an electrical field, there is perpendicular to it a magnetic field that's associated with it. So if this acceleration is periodic, if an electron, for example, gets bounced back and forth in some regular repeating fashion, the electrical field that's generated has frequency to it, and that electrical field is going to be cast off and move through space as a wave. This little demonstration might give you a better understanding of how electromagnetic radiation is generated and travels through space. One of the forms of electromagnetic radiation is radio waves. Radio waves originate in a radio antenna. So at the radio station, electrons dance up and down according to a prescribed dance that the electronics inside the radio station make them do. And because they're charged particles and they're being accelerated, they're generating this traveling field variation that moves through space. So looking at this electron here, I can cause this electron to move, and as I do that, it casts off a changing electric field that you can see moving through space. Move the electron. Anytime it accelerates, it casts off a wave. Now I'm going to change the settings of this demonstration and cause it to oscillate automatically. So this is fairly low frequency. I've got this electron moving up and down, and notice how the field doesn't track with it. When the acceleration is the greatest, the field is the highest. So the acceleration is greatest when it's coming to a stop and starting back up again. When it's in the middle of its motion, its acceleration is the smallest. So you'll see that happening if you're watching the arrows. Now as it travels through space, a change in this electric field occurs in the places where it's going. The magnetic part of this electromagnetic radiation isn't shown in this demonstration, but perpendicular to the electric field wave that we see here would be a magnetic one that's in phase with it exactly, but 90 degrees from it. Now if you look at the antenna on the little house on the right here, that antenna is a receiving antenna. So that's a radio antenna for a radio receiver. like you'd have on a portable radio that you might own. As the field travels through that antenna, the electron responds. Notice that it changes and goes in the direction that the arrow is pushing. So that electron is following the changing field. So the dance that's created by the electronics at the radio station is duplicated by the electronics in the radio, and the signal that's being sent out by the radio station is received and translated by the electronics in the radio. The traveling electric field is accompanied by the corresponding magnetic field. The magnetic field is in the same phase as the electrical field, and it's perpendicular. So this is a sort of an illustration of what these invisible electromagnetic waves would look like. Imagine that the red arrows represent a changing electrical field that's moving through space, and the blue arrows represent a perpendicular change in the magnetic field that's moving through space in the same phase but perpendicular. To get a better feel for what's happening here, look at one particular arrow and then lock your eyes there in that space. Don't follow the arrow, just look at the space. What you see happening is arrows are constantly moving past you, but they're bigger and smaller, and oscillating between up and down. So if you're another electron and you're sitting in one particular spot, the attraction that you're going to feel is constantly going to be changing. It's going to be getting weaker and stronger, and it's going to be pulling you up and then down. This electromagnetic radiation all travels at a constant speed. It's called the speed of light. In a vacuum, when there's no interference from any matter, that speed is 2.998 times 10 to the 8th meters per second. Now, because we happen to know that speed, which is the speed of light, is equal to lambda times nu, or wavelength times frequency, we can answer this question. What's the frequency of yellow light that has a wavelength of 625 nanometers? So frequency is what we're trying to find, nu, so we'll solve for it. Nu is equal to speed of light divided by lambda, or the wavelength. So the speed of light is 2.998 times 10 to the 8th meters per second. I'm going to divide that by lambda. Lambda is given to me as 625 nanometers, but since my speed is given in meters per second, I'm going to convert that. 625 nanometers is 625 times 10 to the negative 9th meters, because there's a billion nanometers in a meter. With my meters now canceled out, I'm going to get units of 1 per second, which is hertz. When I do my calculation, the answer that I get is 4.80 times 10 to the 14th hertz. Now, a hertz is a cycle per second, or vibration per second. So what that means is whatever vibration caused this light, this yellow light, that vibration was happening close to 1,000,000 billion times a second. One of the things that clued scientists into the idea that this might be a way to investigate what's happening with the electrons in the atom is they couldn't imagine anything small enough that it could vibrate that fast unless it maybe were an electron. This is what's called the electromagnetic spectrum, and it shows all the electromagnetic radiation that's available. The visible light that we're familiar with only represents a small part of the total electromagnetic spectrum, and it ranges from about 400 nanometers, that's about the shortest light we can see, the violet stuff, up to about 700 nanometers. That's the longest light we can see. So it's a very tight range. To put this in perspective, infrared radiation, which is the stuff that's just too red for us to see, ranges up to about 0.03 centimeters, which is 1/10 of a millimeter. That's getting fairly long compared with 700 nanometers. And radio waves, which includes microwaves, can range all the way up to 30 meters, which would be extremely long by comparison. If it's too violet for us to see, we have this region that we call the ultraviolet spectrum, and that goes down to 3 nanometers. So from 400, which is what we can see, down to 3 nanometers is ultraviolet radiation. And then X-rays is the next shortest bit of the spectrum. This boundary is a little bit fuzzy here between X-rays and gamma rays, but that goes down to about 0.3 picometers. A picometer is 10 to the negative 12th meters. So this is getting extremely short, and then gamma rays are even shorter than that, most of them. Now the shorter the wavelength, the higher the frequency, because speed ties those two together, and they're inversely proportional to each other. So what are the frequencies like? Well, the X-rays are on the order of about 10 to the 12th hertz. So that's about a million cycles per second. Something's vibrating that fast to cause that to occur. The visible light is about on the order of 10 to the 14th hertz. So that's about 100 million vibrations per second. And the longest waves, those really long radio waves, have a vibration frequency of 10 to the 4th hertz. So that's only 10,000 times a second, which seems really fast, but compared with 100 million times, it's very, very slow. So that's kind of the range of the electromagnetic spectrum. Here's another illustration that might help. This is a sort of a cartoon of a microwave oven, and we can get an idea of how microwaves heat up food by looking at the response here. Right now the microwave is off. The flat green line in the middle of the microwave is the 0 position, and we're going to begin to oscillate this by turning the microwave on. There's a water molecule in there. Water molecules have polarity. One end is slightly positive and one end is slightly negative. So as the changing electric field passes through the water molecule has a response. Take a look. That water molecule starts jiggling around, starts spinning in response to the changing field that's passing through it. Let's put more molecules there. We're going to start out with a row of molecules and turn it on. Now they're not only spinning around, but as they spin around, they hit each other, and then they start moving, bouncing around inside the microwave. As they start bouncing around, they occasionally are affected by the field because they're real close to it, and they bounce into each other. If you look at the thermometer off to the side, you can see that there's a lot of energy being put into these molecules. Here's a cup of coffee. Let's turn on the microwave. Now these particles are jiggling around, banging into each other. Enclosed in this small space, they're also banging into the cup, and you can see that their motion is now much higher than it used to be. The thermometer tells the same story. Over on the left-hand side, you see the thermometer showing very high temperature. So electromagnetic radiation carries information, and it carries energy in the fluctuations of this electromagnetic field wave. Now we've looked at electromagnetic radiation as if it's a wave, and in fact a lot of times it does show itself to us using wave-like characteristics. In fact, some experiments that physicists did showed that it really matches how, say, water waves or sound waves behave, but they didn't all tell that same story. In fact, here's an example. This is called the photoelectric effect. Now the photoelectric effect is when you shine light on an object, piece of metal typically. We're looking at sodium here in this simulation, and that light ejects electrons by destroying an atom, tearing an atom apart, and causing it to yield up some of its electrons. And the electrons then will move across this circuit that's shown in this little diagram, and you can see that there's a current flowing if you look down in the corner at this little current box. It's like a current meter. Now here's the weird thing about this. If light really is a wave, and if you think about how waves behave, a big wave causes more destruction than a small wave. That's the thing that causes the most damage. So a 10-meter high tidal wave that comes and hits your house only once every 10 centuries, that's going to smash your house at very low frequency once every 10 centuries. If you have little teeny waves that have high frequency, like one hits your house every second, that's not going to destroy your house, except maybe slowly by erosion. So thinking about wave phenomenon, big intensity or big amplitude should cause lots of current to flow, and low intensity, no matter how frequent, should cause very little destruction. Let's watch what happens when we fool around with this. Right now we're at this kind of bluish light. As I move this toward the ultraviolet end and the frequency gets higher, I'm keeping the intensity exactly the same, but you can see that the current jumps way up. Before it was at about 0.01 something, and now it's at 1.4. And you can see the electrons are moving way faster too. Now if I dial the intensity down, almost down to 0, if I dial it down to 9% of the maximum possible, I'm still producing quite a bit of current, 0.13, more than I did even at high intensity at the lower frequency. Now at this low intensity, watch what happens as I move toward the higher wavelength end of the spectrum, the lower frequency end of the spectrum. At some point I cross a boundary and I just stop seeing electrons at all. So I'm down here in the red region and I'm not getting any electrons. So what should I do? I'll crank up the intensity. So I'll put this all the way up to 100%. Still no electrons are flowing. So this is exactly the opposite of what waves would tell us. Wave theory would say the bigger the amplitude, the taller the wave, the higher the intensity, the more current you're going to get because you're going to destroy more atoms with a big, powerful, high amplitude wave. And it doesn't really matter what the frequency is. But here we're seeing the intensity doesn't matter. It's the frequency. Everything's about frequency. These low frequency waves don't do anything. The high frequency waves, even at low intensity, can still produce current. That photoelectric effect is one of the things that led scientists like Max Planck here to propose that electromagnetic radiation appears as both a wave and a particle. This is called the wave-particle duality of light. Albert Einstein later on gave these particles a name. He called them photons, and he showed that you can quantify the amount of energy that each one of these little particles, these little packets or photons of energy would have. It's given by this number here that's called Planck's constant, named after Max Planck, times the frequency. And Planck's constant has this value. It's 6.626 times 10 to the negative 34th joule seconds. So when you multiply this by a frequency that's in 1 per second, you're going to get joules, which is energy. Every one of these photons carries a certain amount of energy. And the higher the frequency, the more energy it carries. So that explained the photoelectric effect. Not wave phenomenon, but particle phenomenon. Well, next time you're going to see how this study of light is related to what's going on in atoms. And this background hopefully will help you understand that better when the time comes.